Okay, so the thing is that many inverse problems actually have nonlinear operators. I will mostly concentrate on MR velocity imaging and diffusion tensor imaging, which are visualized here, but I will talk about them later. Of course, the nonlinearities pose many difficulties to the numerical solution of these problems. And in imaging problems, in general, there are also various other challenges. For one, the regularizations that we use in imaging, like total variation and so on, are non-smooth, which is difficult for optimization methods, especially conventional methods. And then imaging problems are quite big. If we consider this as a simple typical photograph, current digital cameras are at the range of 20 million pixels at the moment. We get similar amounts of data in MRI as well. MRI resolution is not huge. It's like 256 times 64 volume would be quite high by today's standards, but in diffusion tensor imaging we have 6 values per voxel basically, and that also brings the count to somewhere above 20 million. So the problems are relatively large, and this creates computational challenges. Further challenge is that in imaging problems, the visual quality of the solution is quite important. PSNR or norm convergence is not really a good indicator of quality. There are examples where you have 2 images with the same PSNR. One looks awful, one looks good. And this kind of things also affect the choice of algorithm that we want to use. Some algorithms, like a basic gradient descent algorithm, does not really produce good-looking solutions. That's why you want algorithms that are good. One rather good algorithm based on practical experimentations is the Champolle-Bock algorithm. It's becoming quite popular in imaging, and that is why I also concentrated on that for the MRI applications. Let's look at this in detail. In diffusion tensor imaging, we take multiple images of, let's say, the brain. Here we have 9 different images. One image which has the highest contrast here is like a normal MRI image, but the other images are kind of diffusion weighted images. You apply a diffusion sensitizing gradient to the measurement, and this makes the measurement sensitive to the movement of water molecules along this gradient, and this way you can measure how water moves in different directions, and you can combine these multiple different measurements through the statistical Tanner equation displayed here into a diffusion tensor image, where at each point or each voxel in the brain you have a tensor which describes the probability of water diffusing in different directions. It's basically just a covariance matrix of a Gaussian distribution at that point. It's difficult to visualize. Usually it's visualized by color coding the principal eigenvector of this tensor like this, or you can just also visualize its ellipsoids, which are basically the confidence ellipsoids of the distribution, but that way you can only display small volumes. How is this useful? One way to make this useful is to perform so-called tractography on the principal eigenvectors. So you follow the principal eigenvectors to find neural pathways. This works very well in the white matter of the brain. In the white matter, if you consider the ellipsoids, they look like this. There's a single clearly defined principal eigenvector. In gray matter, the ellipsoids look more like this. There's no single most probable direction. And this is related to the fact that the white matter transmits information in the brain. And doctors can, for example, see if there's something wrong, if there's a deficit in white matter, and that will alter the tractography results to have anomalies. And now, MRI devices are not very great. They have noise, and of course, they're slow, so patient movement can alter the results. That's why we need some kind of processing of the images. I will only concentrate on denoising here. And there are some requirements for the procedure. One thing is that, of course, because we are dealing with probabilities, the tensors are covariance matrices. They should be positive definite. There's no negative probabilities. So the procedure should preserve this kind of things. And the procedure should also be rotation invariant. It shouldn't matter if my head is like this or if my head is like that, what the results really are. That's one feature that affects the choice of the finite dimensional norm in our method, similarly to what we discussed about color TV and so on. And then, of course, physiological features of interest should be preserved. That's more vague notion that medical experts have to define. That might bring us to really more these kind of domain-specific regularizers that were mentioned in the previous talk. And in the mathematical approaches, there are some things like log-Euclidean metrics, which are theoretically very attractive because they just basically allow you to map the positive definite cone of the covariance matrices into the whole space, and then do some standard total variation or whatever in there. And they also have the attractive property that they basically preserve the volume of these tensors, but they may change the shape of the tensors, so they do not really preserve gray matter and white matter so well in our experiments. There are also some Riemannian flows, kind of paranormalic approaches that have the blow-up problem that these kind of approaches have. And you could just denote each of the different source images separately, but we want to exploit the tensor structure. So what we do is we study the typical Tikhonov regularized approach, where you have a forward operator and a noise model phi, our data and the solution you are looking for, and apply some regularization functional there. What could the noise models be? If we start from the ground up, MRI measurements are in the so-called case space, which is basically the Fourier transform of the image. And if we incorporate the Fourier transforms and also our Seiskal-Tanner equation into the model, we get a rather complicated nonlinear model, where we also have the positivity constraint. So this is a difficult problem. You can simplify it a little bit. And actually, usually how you get data for diffusion tensor imaging is just the absolute values of the inverses of the Fourier transform. So these are the diffusion weighted MRI images. And we could use these to get a little bit simplified model, which is still non-convex. There's a nonlinear operator in the fidelity term. And now in this case, this squared L2 noise model is justified because it corresponds to Gaussian noise. And these images have a risen noise. So we might want to, and this is still a difficult problem, it's non-convex, so we might want to simplify it further. We can actually kind of linearize the Seiskal-Tanner equation, taking the logarithm out of it, and then just solve some tensor field from that and denoise that. That was our first approach because we just wanted to basically do total generalized variation on tensor fields. So that's what we did. It works, but the noise model is completely wrong in this case. You can also somehow incorporate, get rid of this nasty and wrong middle step of solving something from regression from this by incorporating the linearized Seiskal-Tanner equation as a forward operator. Again, noise model is wrong, but we have a simple convex problem that we will later compare against this second nonlinear problem, which is the easier one. But let's look at the other application now, which is MR velocity imaging. In MR velocity imaging, the basic idea is somewhat similar to diffusion tensor imager or diffusion weighted MR imaging. We take MRI measurements where now somehow the velocity of a fluid in a certain direction, again the kind of gradient to which we make the measurement, is encoded into the difference of the phases of two images. So the data is now complex. Here we see a fluid flowing in a tube and a bubble there, and we can study the behavior of the fluid around the bubble and the movement of the bubble by studying the velocities of the fluid in the tube. These are applications in chemical engineering, studying all kinds of packed beds and so on, and also in medical imaging, in the imaging of blood flow in the body. So many applications. Now, the difficulty with this kind of things is that if you have something moving, you really need to make the measurements fast because the situation may change, and that's where we get into compressed sensing. So we only make partial measurements. You may not see it very well here, but here we have like a full case-based image, full Fourier transform. Here I have only applied like a spiral sampling pattern, so only part of the samples are there. Now, if we do a simple inversion of the problem, just inverting the Fourier transform, this is what we get for the synthetic data with full data, but this is what we get with the partial data, and especially the amplitude looks quite bad here. It has lots of noise and it's lost the piecewise constantness. So that brings us to the priors or regularizers that add some information to the problem that we know what we think the solution should look like, and we want to apply that to this. What should these regularizers do? In imaging generally, regularizers should restore smooth areas correctly, and they should also restore geometric features correctly. Geometric features would be, in this case, for example, these pebbles here. You really have edges between the pebble and the fluid, especially in the amplitude. You can see it very well. This is piecewise constant, and these are geometric features that we want to restore. In many imaging applications, you would want to restore texture, especially in photography. Not in this application really, but in the diffusion tensor imaging application, you would want to restore some physiological features of interest correctly. This is again not so exactly defined. It's domain-specific information that doctors have, and in this chemical engineering application or so on, you want to restore physical features of interest correctly, for which you have physical models, which may be very complicated, like the Navier-Stokes equation. But we just concentrate on typical regularizers for imaging here, which are wavelets, and of course total variation, and something more recent, which is second order total generalized variation. This avoids the staircasing effect of total variation, as we will see. And we have extended them to tensor and complex cases, which we use here. So here are the results on a small part of the original image. Again, the upper row has the amplitude, the lower row has the phase. We have the simple back projection here, and wavelets. Wavelets have a lot of artifacts. At least the dopage is 3 or 4, was it? Yeah. And then total variation works very well. For the amplitude, it's almost restored the piecewise constantness, because total variation likes piecewise constantness. But it has a lot of staircasing effects in the phase. And the total generalized variation completely avoids the staircasing in the phase. It does almost perfect reconstruction of the phase, but it does have another artifact. It has kind of slanting effect. So if you use total generalized variation on a simple step function, the corners tend to be like this. And there's a slanting effect, which you can see in the amplitude around the pebbles here, if you look carefully. What this suggests is that we should do separate regulation of the phase and amplitude. We could use total variation for the amplitude in this case, at least for the synthetic data set, and use total generalized variation for the phase, and then we would reconstruct the complex image from the components. Now, this is again a nonlinear model. We have a nonlinear forward operator in this problem. How might we solve this? We can rewrite it a little bit. We can write this squared L2 fidelity in terms of an additional dual variable like this. We maximize over the dual variable, add something extra there. And if we can also write the regularizer similarly, basically in terms of conjugates and so on, we get into this kind of, in a sense, saddle point problem. We have a convex function here, another convex function here, and then this kind of saddle term, where now if the operator k in this term were linear, we could use the Champollion-Bock method, for example, to solve it. But in our case now, through this transformation of the problem, moving this a nonlinear operator here into the operator k here. K is also nonlinear. Could we still use the sample epoch method for this? Actually, we can. Let's look at the method. The sample epoch method is also otherwise known as the modified primal dual hybrid gradient method. It's a primal dual method that is based around backward or proximal steps and some inertia step that makes it convergent. Without the inertia step, the method isn't necessarily convergent. So we first do like a proximal step or a backward step on the primal variable, basically keeping the dual variable fixed in this problem here. Then we apply some inertia to it, and then we fix the primal variable and do the backward or proximal step on the dual variable. And now the optimal conditions for this saddle point problem look like this. In the linear case, we just have these inclusions of the operator applied to the dual variable in the subdifferential of this function, and similarly for the primal one. For the case of a nonlinear operator, we get similar optimal conditions, which can be shown to be necessary under mild conditions that are usually satisfied, especially in this case of squared L2 fidelity reformulated in this form. They're a little bit more complicated, but there's lots of correspondence here, and you can see similar terms here in the algorithm. So could we just replace these blue parts by this blue part here, and similarly for the red part, and get a convergent algorithm, which would look like this. We again do a simple linear operation here on the dual variable, backward step, inertia. Now we keep this application here on the primal variable nonlinear, do some backward step and so on. And here we didn't do any linearization. We can also do that, just using Taylor approximations. And it turns out that this modification is easier to analyze, but computationally slower. The convergence rate in experiments is actually exactly the same for the two variants, but this is, at least in the applications that I've looked into, faster because this operator is easier to compute than this linearization. But the analysis that I will talk about is based around this form of the problem, which looks more complicated. To see how we might prove the convergence of this method locally, of course, let's write the original sample epoch method for linear k as a proximal point method. Proximal point method basically solves at each step of the method this kind of variational inclusion where you have a monotone operator and then difference between the iterators and some operator applied to it. In basic proximal point methods, this operator M is just a step length parameter times the identity. But in other cases, it can be seen as a preconditioning operator or preconditioning matrix. And we look for ui plus, and now writing x and y as u here. And in the case of the sample epoch method, this monotone operator just basically comes from the optimality conditions. This is not maximal monotone, so it does not come from a convex minimization problem at all. And the preconditioning operator looks like this, where you have some step lengths and this operator here. And yeah, this is the optimality condition. Well, we can do similar thing for the nonlinear method. Now, it's a little bit more complicated. First of all, at each step, we basically consider a local linearized problem. So now the monotone operator depends on the current primal variable. So likewise, the preconditioning matrix depends on the current primal variable. And then we have kind of discrepancy term here, which, and this is the important thing, for the linearized method is 0. So we don't get this nasty discrepancy term. But for the original, what I call the exact method, we get the nasty discrepancy term, which is O2 in the step length. And we want to get rid of it. It can be done, but it's not too difficult to do. So this argument here is basically proving convergence for both of the methods. And it's based on a kind of a bridging argument through many different variables. let's say we have our problem here. This is our function we try to minimize. This is the true solution u hat, and our iterate ui is here. Then we linearize the problem locally here, and we might get that the problem is a local solution u hat I when it's linearized. But through this whole perturbation thing, we have kind of local perturbed solution, which might be different from u hat. And in a sense, now the step moves toward this perturbed local solution. So ui plus 1 might be somewhere here. And now we have to kind of estimate the distance from here to the real local solution with the help of this perturbed local solution, and then further to the real solution of the problem. This kind of bridges through all of them. So how might we do? First of all, we use the monotonicity of our operator, and we also assume some strong convexity in some subspace to get this kind of estimate where we have the distance to the current perturbed solution of the current iterate and then the next iterate. And these norms are kind of local based on this preconditioning matrix. And what we want to do now is, first of all, here switch the preconditioning matrix to the next one, and same with the perturbed solution, and also switch from the perturbed solution to the local solution, and so on. We can do that using this thing that we get from the strong convexity. We can eliminate this bar and add some factor here, and so this way switch to the next local metric at the next point, correct metric at the next point. Then we need the so-called open property of our monotone operator, or its inverse, which is it's a set-valued Lipschitz property. We won't go into the details of that. And using that, we can remove the squares. This is just a technical step that's necessary to move to the next part. And still using the open property, we can now do the bridging. So we finally get rid of the perturbed solution at iteration I, and on the left-hand side, replace the real local solution at iterate I, and on the right-hand side on the next iterate. And this now starts looking good. This is a telescope property. This here corresponds to this here, but at the next iterate, and we have the step lengthening here. And from this, it's not difficult to prove convergence anymore. Now the critical part is really we need this discrepancy to go to 0. That's not difficult. But then we also need the open factor to be small. Well, the open factor is small if the noise level is low. No, it is not small, but the nonlinear part of the dual variable which just corresponds to our noise model, or the distance between that can be made small if the noise level is small and the regulation parameter is small. Here we have results on velocity imaging. The algorithm performs much better than Gauss-Newton method, which takes lots of iterations and lots of time. Our method is fast. And also comparing the different noise models. This is the nonlinear method here, nonlinear model here, and these are linear different solutions, different regulation parameters chosen by discrepancy principle or PSNR. It seems that PSNR choice gives by PSNR itself best results, but actually the amplitude looks very bad, and this here has staircasing, so we may scratch them. The nonlinear model works best. Same for MRI. Gauss-Newton is much slower. In some cases, doesn't even converge. The nonlinear sample epoch works very well. Comparing again using discrepancy principle or PSNR to choose the optimal parameter, it looks like with the discrepancy principle as stopping criterion, PSNR as stopping criterion, the linear model might work best. But if you look at the corresponding solutions here, the PSNR choice has chosen a very bad parameter. That's the over smooth the solution. So PSNR is not a good criterion. Discrepancy principle works very well. So we can scratch them, and again, the nonlinear model, at least in terms of PSNR and discrepancy principle, works the best. Okay. So what we can conclude is that nonlinear models improve MRI reconstructions. The nonlinear sample epoch method works very well. It would be interesting to look into how we could extend this to iterative regularization, because Gauss-Newton is used a lot in that context, and also Bregman schemes, which are a type of iterative regularization. There are a few publications about that. The algorithm publication is not yet published, but hopefully soon. The other earlier works are here. That's the last slide.
Well, I've got two short questions. First, you said that there are some physical constraints, like the, for example, rotational invariance of the tensors and positive definiteness. So when you solve the optimization problems, you end up with constrained optimization problems. How do you encode
This kind of rotational invariance is not really constraint in the problem. Is just how you define your regularizers. So the regularizers should be invariant restrictive directions. Like if you have simple total variation, here is this some norm here, dx. This is the finite dimensional norm. If you use the one norm as the finite dimensional norm, then you get anisotropic TV, which kind of prefers edges in these directions, because that's the shape of the unit ball in that norm. But if you use two norm, then the unit ball looks like that, and you get isotropic behavior. And it's the same with extensions to tensor fields. Now you use the Frobenius norm, or you could use something called the largest or smallest reasonable cross norms, which are equivalent to nuclear norm or spectral norm for matrices. But you have much higher order, and these are not computationally viable.
So you still have unconstrained optimization problems?
Well, not for the positivity constraint, not.
Yes,
yeah. Positivity constraint is easy to handle in the sample epoch method. In a sense, it's just a projection. You need to do some QR algorithm stuff to project to the positivity cone, but that's not too bad.
Okay. And the second question, when you're talking about noise models, do you assume statistical noise or deterministic noise, just as an error in the given norm, or do you assume a distribution of the error?
Basically, I don't deal with the statistical part really, but you can kind of map all of these usual Tikhonov schemes into a statistical probabilistic framework, where the squared L2 fidelity term just corresponds to a Gaussian noise distribution, and the total variation so is then the prior distribution.
One last question. You mentioned in one of the experiments that TV is good for magnitude R, TGV is good for phase phi.
Yeah.
And that's a bit strange, because TGV has a ratio parameter. If you do a bit tuning, you can do both.
Yeah.
You can do both. Yeah.
Okay. The thing is that now in this linear model, we only have one regularizer for the whole complex images, like TGV extended to complex valued images. So you cannot tune the two components separately. If you get good amplitude, you get bad phase. So you can tune TGV to perform basically the same as TV, but then you get bad phase, and so on.
All right. Thank you very much, Timo.
Thank you.